Hello, everybody. Thank you. Nice to see everybody again in our final lecture in our 20th anniversary series. I hope people have enjoyed it. I think it's been a really interesting series. And tonight's lecture will definitely be not an exception to that. So before we start, let me just do my usual. I want to thank the folks at the Huntington for hosting us, this amazing space. It's really, I was talking to Wendy and saying how wonderful this stage is to give a talk on. It's really quite nice. You can see kind of everybody, and it's just a really warm space. So thank you for them for all their help. I want to acknowledge all the wonderful musicians. Tonight's were, every time it's more and more exceptional, I think. And so thank you again. And thank you to Erica Clark for organizing all those. Right there, Erica. And I want to thank our other Carnegie volunteers who you see all the time, Natasha, Jeff, Gina, Beverly, and a few other random postdocs who show up to help us with that. They make it very easy. And finally, I want to thank the Norris Foundation, which provides funding for this and allows us to use this space. So thank you to them. Okay, on to today's speaker. This Wendy Freedman is, I think, a really well-known quantity to many of you. I was hanging out for a while, and a lot of you were super excited walking in, which is great. And that's because, of course, she spent a good fraction of her career right here in Pasadena at Carnegie. So Wendy finished her PhD at the University of Toronto back in 1984, and then she came to Carnegie as a prestigious Carnegie postdoctoral fellow. 3 years later, she joined our staff. She was our first female staff member at the observatories. Yeah. and then in 2003, she became our 10th director, which was, of course, very exciting. And as director, one of the things she did, which you can even see on this image here, of course, was she really initiated the giant Magellan telescope, which many of you heard about. It's been in most of our talks for a long time. And this is such an important telescope to our future. And Wendy really deserves the credit for really making that project happen. In 2014, Wendy stepped down from being director at the observatories, and she moved on to the University of Chicago, where she is the John and Marion Sullivan University Professor of Astronomy and Astrophysics. She's, of course, really well known for her work on the Hubble Constant, which you're going to hear about tonight, which, of course, has its origins right here, once again, at Mount Wilson and at Carnegie, a long history here. I always give talks, and I always say that Wendy's really was responsible for really the first precise measurement of the age and size of the universe. Her measurement of the Hubble Constant really gave us that measurement, and you're going to hear about that today. What's really remarkable, which you'll hear in the talk tonight, is just how accurate we're getting to understanding the Hubble Constant. Wendy is a recipient of many honors. I'll just read a few of them here. She's a member of the National Academy of Science, a fellow of the American Academy of Arts and Sciences, a fellow of the American Physical Society. She's also a legacy fellow of the American Astronomical Society. In 2009, she shared the Gruber Cosmology Prize, which is a huge prize given in cosmology. And that's just a partial list of her many, many honors. And so with that, let me just welcome her to the stage. Wendy Freedman, everybody. Wendy.
Thank you for that introduction, John. It's a pleasure to be back here in Pasadena. I spent most of my adult life here, raised a family here, spent most of my scientific career here, have still very close friends here, some of who are in the audience, and I'm delighted that they're here this evening, and maybe even colleagues that I haven't seen yet. So it's a pleasure to be back. Well, just the year before I became director, in 2003, so in 2002, the former director, Gus Omler, and a small committee of us planned this series, and it's amazing to me that 20 years later, it's still going strong. So it's a testament to John and to Erica. And of course, much of cosmology began in Pasadena, and our view of the cosmos, our perspective on the cosmos, our understanding of cosmology and the universe in which we live began right here in Pasadena. And of course at Mount Wilson, where Edwin Hubble began his work, and leading up now over a century later to the giant Magellan telescope, which has really been a successive series of telescope building that was begun here in Pasadena. And so it really was an unknown astronomer, now a century ago, literally 100 years ago, 1922, who was using the Mount Wilson telescope and taking a series of glass plates. And I realize that in the audience there are probably people young enough who have no idea what an emulsion is or what a photographic plate might be. But at the time, the only detectors that were available in astronomy were big, large glass plates that were covered in an emulsion that got exposed to the sky. This astronomer went up to Mount Wilson and took a series of plates of objects that were called nebulae at the time. And nebulae are, at that time, nebula is a word that means fuzzy in Latin. And at that time, there was a debate about what the nature of these nebulae were. And the question that people were asking was our Milky Way galaxy the entire extent of the universe, or were there other universes like the Milky Way that were at much larger distances? And there was no way to know that because there was no way to measure how far away any object was. So if you look up at the night sky, you can see in 2 dimensions that there are stars and objects in the sky, but that third dimension, the distance, there was no way of gauging that. And so this astronomer was taking plates, probably around now, and then the glass plate that changed the world, I think I went one too many, yes, is this one. And here is the 6th of October, 1923, and you can see this wonderful blob, black blob here in the middle. It's obvious that that would change our perception of the universe, right? You might even be able to see these little black dots here. So this is a negative image, and stars are black in this image. You might even be able to see some white streaks that are going through here. And what Hubble, now we know who that astronomer was 100 years ago, what he did was he recognized that this little pinpoint here, and he had labeled it originally with an N for nova, or a new object, or people originally believed were new stars. They would brighten. And he realized at this point that it wasn't just an ordinary star that was changing in its brightness, it was a variable star, and a particular kind of variable star called the Cepheid variable. And these were stars that had been known since the 1700s to change their brightness over time. And they didn't do it in a way that was erratic. Rather, they did it in a very cyclic way, so that they would rise in their brightness slowly, and that even more slowly, they would decline in brightness over time. And so they did this up and down variation, sort of like a seesaw. And having recognized that he had found a variable, it became clear to him that he could now measure this third dimension, because these Cepheid variables have a property that let you determine their distance. The rate at which they vary is related to how bright they are. And once he realized that, he was able to show that they were not objects in our Milky Way galaxy. They were much farther out. And then he went on to show that they were actually moving, and most of them were moving away from us. So literally, this was the glass plate that changed our perception of the world. Together with Albert Einstein's general theory of relativity, it led to our picture of an expanding universe and a Big Bang, an early hot origin for the universe. So here is Hubble 30 years later, examining a plate. My guess is it's not this plate. And my guess is some photographer asked him to pose. But this is the plate where he recognized, at least in Andromeda, and in fact, he made his first discovery of Cepheids in a galaxy called NGC 6822. I don't think it has the same ring as Andromeda, and so no one really realizes that Andromeda was not the first galaxy that he discovered Cepheids in. Okay, so a little bit more of Pasadena history. And if we go back, how did Hubble come to make these observations? The astronomer George Ellery Hale came out to Pasadena in 1902, I believe, and he was very interested in building new large telescopes and very interested in Mount Wilson as a site. So Mount Wilson at that time had much darker skies, and property we now appreciate, astronomers appreciate, called seeing. It's a very steady atmosphere that doesn't do much blurring of the images of stars or other objects that are coming to us from distant space. And George Ellery Hale had a nice phrase. It was actually quoting the architect in Chicago, and what he would say is, make no little plans. And he lived true to that statement, because he came out and he built the solar tower at Mount Wilson. Then he built the Mount Wilson 60-inch telescope, eventually the Mount Wilson 100-inch telescope, and then the Palomar 200-inch. He was the mover behind that telescope also. And so, and he had built the Yerkes telescope outside of Chicago in Wisconsin, in fact, before he came to Pasadena. And when he came to Pasadena, at that time, there were no paved roads, there were dirt roads, very small population. His family was not thrilled with coming out here, and, but he really revolutionized astronomy, the world of astronomy. And also within Pasadena, he was responsible for bringing out the architects that built the City Hall. He convinced Henry Huntington to put the Huntington Library here in Pasadena. We wouldn't be here tonight if it wasn't for George Ellery Hale. Originally, Henry Huntington had wanted to put his art collection in LA County. And so a man of enormous influence, and interestingly not well known today, but had a huge influence. He also was the person responsible for our main journal in our field, the Astrophysical Journal, and the arm of the National Academy of Sciences, the National Research Council, that is the arm that advises government on issues having to do with science. So an incredible person. He was the first director of Carnegie, and an inspiration for me. He was also visited by an elf, an angry elf apparently, who scolded him. And so anytime I felt that I was having difficulties as a director, I always felt that I was lucky compared to George Ellery Hale, because at least I didn't have an elf. So I stepped down at the right time. Poor John inherited the role. Now, so Edwin Hubble made these observations of these extragalactic nebulae, and of course today his name is known over the world with the Hubble Space Telescope that, again, really revolutionized what we could do in astronomy. And so here's his, whoops, this likes to go without me telling it. This is the diagram that allowed him to determine that the universe was expanding. So this is velocity going up in this direction and distance increasing to the right. And what he found was that when he started measuring these distances using Cepheid variables for the nearby galaxies and other techniques a little farther out, that the farther away a galaxy was from us, the faster velocity it was moving at, and farther out, higher velocity. And there were a handful of galaxies that had negative velocities, that is, they were approaching us, and it turns out Andromeda is one of the very few. But by and large, the galaxies in the universe are expanding, appear to be expanding away from us, and that together with Albert Einstein's general theory of relativity, which allowed for an expansion of the universe, gave rise to the picture of a Big Bang. That is, the universe, if it has been expanding for some time, if you, in a sense, wind the movie back and reverse, you would end up with a very dense universe, very hot universe early on. And that led to this picture of a Big Bang cosmology. So here is Einstein. This photograph was actually taken in the library at Santa Barbara Street, the Carnegie building here in Pasadena. And Hubble here is showing Einstein how to use the telescope at Mount Wilson. Einstein came for a visit in 1931, and of course, we all smoke pipes when we go to the telescope. Okay. So the other person who really deserves a lot of credit for this early work is Henrietta Leavitt. And in fact, all of the work that we do now still builds on the foundation that Henrietta Leavitt and her discovery of a relationship between the rate at which a Cepheid variable is changing in its brightness and the brightness itself. And so this relationship that she discovered allows you, if you can determine what the distance to a nearby Cepheid is, say in our own Milky Way galaxy, then you know how bright it should be for a given period. Then you go out, like Hubble did, or like we have done with the Hubble Space Telescope, you measure Cepheids in another galaxy, and simply by using the inverse square law of light, that allows you to determine its distance. And so Henrietta Leavitt, who was working at the Harvard College Observatory, made this discovery in 1908. And so when we began our work with the Hubble Space Telescope, after the Space Telescope was launched, we used these same Cepheid variables. This is one of the best means we have today of measuring the distances to galaxies, enabled by this discovery of Henrietta Leavitt. And then we've also made observations using the Spitzer Space Telescope that works at infrared wavelengths to allow us to get away from the dust lanes that you could see in the earlier photograph that I showed you. They're dark in this image, but the dust that is formed in the atmospheres of younger stars gets expelled back out into the regions between stars and then blocks the light that's coming to us from the stars we want to measure. So that's a real challenge for us to actually correct for the presence of dust, and one of the reasons why Hubble's original measurements ended up much larger, the rate of expansion of the universe, than we measure today. Okay, I have to go 2 forward and 1 back. This is what we now refer to as the Leavitt Law, the relationship between how bright a Cepheid is. So this is brightness going up, and then the longer periods going to the right. And you can see this really nice, tight relationship between how bright a Cepheid is and how fast it's varying. And that's what allows us to measure these really accurate distances. And that gave rise to this field of observational cosmology, that we could actually go out and make measurements and test our ideas now of how the universe is evolving with time. And they actually now let women go to the telescope. So Henrietta Leavitt did not. Henrietta Leavitt did not have a position at Harvard. I think it wasn't until the 1990s that the first woman was hired onto the astronomy faculty, after there was one in the 1940s who was paid 25% of the salary of the men at Harvard at the time. Some things have really changed. And that's given us a means of now moving out from the Milky Way and measuring the distant universe, and actually using the laws of physics that we can measure and test in the laboratory to tell us something about the evolution and the composition of the universe at large. I want to mention that my longest standing collaborator in all of the efforts that I'm talking about this evening is Barry Medor, who also happens to be my husband and father of our children and our now 2 grandchildren, and a lot of postdocs and students over the years that have contributed to this work, but particularly I want to thank Barry. Now, after the discovery of the expansion of the universe, Edwin Hubble, his measurement was around 500 in these units of kilometers per second per megaparsec. I don't expect you to know that, but that's what we use. And you can see that over time, so this is the year since Hubble, here, his measurement here, the value of this expansion rate, so the Hubble constant now, is a measure of how fast the universe is expanding at the present time. And the value came down from 500. There was a big change in the 1950s. Walter Baade, here again in Pasadena, made the discovery there were 2 types of Cepheids, and Hubble, unbeknownst to him, had used the wrong kind to calibrate his value of the expansion rate. And then it settled down, but it settled down to a value between about 50 and 100 in these same units. So Hubble had measured 500. And then for a few decades, the value seemed to oscillate between these values of 50 and 100. And there was a big debate in the field about what was it. And one implied a universe that was 10 billion years old, and the other 20 billion years old. So a factor of 2, we didn't know the age or the size of the universe to better than a factor of 2, which is not a very good place to be. So if you want to know how bright a galaxy is, what its mass is, any of its properties, if you get the distance wrong, then you get all of those other quantities wrong. And so astronomers took to denoting the Hubble constant by a little h instead of this big H that allowed for the factor of 2 uncertainty. And that was one of the reasons for building the Hubble Space Telescope, was to try and resolve this debate about the age and size of the universe. And astronomers recognized at the time that it wasn't going to happen if we were still making observations that were limited from the ground, from the Earth, and that it was necessary to get above the Earth's atmosphere where we could make measurements much more accurately without the blurring effects of the Earth's atmosphere, allowing us to make measurements much more distant than had been possible before. And I'm showing you here, this is where the current state of affairs is, and we'll talk more about that. The argument now is between 67 and 73, or 74, sometimes is claimed. And so you can see that the difference really has decreased. But now what we're talking about is whether or not the uncertainties in these measurements are as small as the thickness of the lines here. So in other words, is this now a significant difference that's telling us something about the universe that we couldn't measure any other way? But first, we're going to talk about how we resolved this factor of 2. And as you might guess, it has to do with the Hubble Space Telescope. And so the telescope was supposed to be launched in 1986. And then there was the terrible accident with Challenger. It was finally launched in 1990. And then it was discovered that the optics of the telescope was out of focus. The focus had only been tested on the central axis of the mirror of the telescope, but not on the whole mirror itself. And so there were a number of years until the optics were corrected. And then, then in 1993, we got our first observations that allowed us to actually begin to make these measurements to improve the measurements of the expansion rate of the universe. And so recalling, here is Hubble's original diagram from 1929. Here's our measurement from the Hubble Space Telescope, also using measurements that were made from Earth, from the ground, using these type 1a supernovae shown here in the green. But the original data for Hubble fit into the first tick mark in this. So it's now possible to go out much farther and to make these measurements a lot more accurately. So the value that we obtained was 72, so in between the 50 and 100 that people had been debating about. Okay. And now what I'm showing, these are values of the Hubble constant in the last couple of decades. So beginning with our key project here, we got this value of 72 with an uncertainty of 10%. So the factor of 2 we overcame with Hubble. And you can see that the value is held pretty steady over the last couple of decades. But what has changed are the error bars. The uncertainties have become smaller and smaller with time. And in the meantime, it's been possible to make measurements of the temperature in the microwave background. And this is an extraordinary map of the Big Bang radiation we now see in microwaves. The remnant radiation that's left after the Big Bang explosion, the universe has been expanding ever since and cooling. And now these variations, the different colors, represent differences in the temperature. And these temperature differences are 1 part in 100,000, so they're magnified. And that's 1/1000th of a percent. That's how accurately now these tiny little differences in temperature can be made. And they're also reflective of variations in the density of the material in the early universe. And these are the seeds that grew to become the structures that we see today, the galaxies and the large filaments and walls and voids that we see in the universe. Anybody see what is in the yellow circle? Well, if you look carefully, there's an S and an H. So when I talk to school kids, this is what I tell them, and it's a message from Stephen Hawking. So together, the measurements of the expansion rate of the universe and now these measurements of the microwave background temperature are giving an age for the universe of something like 13.7 billion years. And the really remarkable thing, so that was an earlier map that I just showed you. This is the most recent map of the cosmic microwave background. So now this new satellite, the Planck satellite, which is a European Space Agency satellite, can make even more precise measurements with more frequencies and better resolution. And in the 1970s, there was a lot of theoretical work that was done to predict what would have happened in the early universe. So you had material at the time of the Big Bang. Shortly after the Big Bang, you had matter, and you had the radiation from the Big Bang. And gravity, of course, is an attractive force, and this radiation pressure was pushing outwards. And it ended up, there were oscillations, sound waves essentially, were formed in the early universe. And these theorists predicted essentially the behavior of these sound waves. And now that it's possible to make these really accurate measurements, this is how well this early theory fits the data. I mean, it's remarkable, this interplay between theory and experiment. I think it's one of the most beautiful experiments in our subject. And encoded within these peaks is information about not only the amount of matter in the universe, and we now talk about dark matter in the universe, we talk about dark energy, there's information about that, but there's also information about the expansion rate. And this is essentially a model, what we now call the standard model in cosmology, and that allows you to predict what the expansion rate today would be given this model and these data. And when you do that, you end up with a value of the Hubble constant of 67. And as I showed you earlier, the values that we get based on Cepheids are more like now 73, maybe 74. So there's a new difference, this difference between 67 and 73. Now, the interesting thing is this a real difference, or are we still looking at uncertainties in the measurements? So this is what happened over time with the cosmic microwave background measurements. So they were agreeing with what we got for the Key project around 72 early on. And then as the measurements have gotten more and more accurate, they've come down. And again, the error bars have shrunk quite considerably, and they've settled in at this value of about 67. Whoops. I could just let the whole thing, I don't have to say anything, it'll show my talk. Okay, so is there a crisis in cosmology, getting back to my original title? And now the question becomes, is this gap that has emerged now, is this telling us that there's something in our understanding of our standard model that is something missing? Is there new physics that we're actually pointing to with the new disagreement in these measurements? So it hinges on whether or not we understand the uncertainties well. I'm ahead. And so when we talk about tension in the Hubble constant, you may have heard this term recently. What we're referring to is this early universe measurements, the measurements of the Big Bang radiation that are giving this value of around 67, and the difference locally measured with Cepheids, where we get a value of about 73. And so the question is, did something happen either earlier in the universe than we can measure right now with the Big Bang radiation, or along the way, say, some physical process that changed the rate of expansion from what we might naively think without adding additional physics? So before I got into that, I wanted to just take a little diversion back to telescopes, because continuing on the theme of George Ellery Hale and building bigger and bigger telescopes, if you have come to this series either early on or the last few years, you no doubt have heard about the giant Magellan telescope. And as John mentioned, this was one of the efforts that I spent a great deal of my time on when I was director at Carnegie. We started off with a small group, 3 institutions, and it's now a 12-institution international project, including South Korea and Australia and Brazil, and now the Weizmann Institute in Israel, Chile, and institutions across the US. But Carnegie was a leader in getting the project going, and still is playing a very important leading role in the project today. So this will be an 80-foot diameter telescope. Will be located in the Andes Mountains in Chile, and on a peak very near the Magellan telescopes, where we currently are observing in Chile. It's the first light for the telescope is now expected to be in the early 2030s, and the mountain is really, the site has been developed, the pier for the telescope has been dug, all the hard rock excavation has been done, and now we're hoping with COVID, now we hope somewhat in the rear view mirror that construction can begin in earnest in the next year or two. This is a telescope that's going to have 10 times the resolution of the Hubble Space Telescope, and it will have 100 times its sensitivity. So it's just one of those things that I really hope before my career is over, I get to use this telescope. It's an amazing piece of machinery. And just to give you some sense of what the telescope will be able to do, if you keep your eye on these big blobs here, this is a simulation of a cluster in a nearby galaxy, and as it would appear on a night of good seeing, that is not much atmospheric turbulence here on the ground. And this is what it looks like with one of the early infrared cameras on the Hubble Space Telescope, so you can see a lot more detail is beginning to emerge. And then this is what it will look like, not yet, with the near-infrared camera on JWST now launched, and our group now has time on this telescope starting in November, so I can't wait. Whoops, no, maybe it did. Maybe you were right. I'm sorry. So this was NIRCam, and this is GMT. But you can see, if you compare with the original ground base, it's just incomparable. It's amazing. So looking forward to that, and remember that because we will talk about GMT, we will talk about JWST, and in terms of resolution, GMT will ultimately beat it. Okay, so is there a crisis in cosmology? Let's come back to that. So I want to make a distinction between precision first. So if we're throwing darts at a dartboard here, and you can see this person is very precise. It's a small cluster of points, but the target, the bullseye, is here, right? So we really want accuracy, and this our field has taken to calling the current time a time of precision cosmology. And my hope is that we're not doing precision cosmology, that we want to be doing accurate cosmology. And so you might not have as great precision, but the important issue is really the accuracy. Are you near the target? And so this is what Barry Medora and I set out to do. We had spent a lot of time working on Cepheids, both before the Hubble Space Telescope, during the Key project, and even after the Key project with Spitzer. But if Cepheids have something unknown, so if there are different parts to a measurement uncertainty, some are things that you know about and you can correct for those, but there may be things that you're not even aware of. And the only way you'll become aware of those is to make the measurement in a different way. You can make the measurement over and over using the same technique, but if there's a flaw in the technique that you're unaware of, you're going to make the same mistake. And so our idea was to use a different kind of star, something called a red giant branch star, and our own sun will evolve to become a red giant. Not for a while, so we don't have to worry yet. And at that time, the atmosphere of the sun will swell, literally become giant. It will enclose, the nearby planets will be within the atmosphere of the sun. And these stars have a nice property, which is that they don't exceed a given limit in their brightness. So once they reach a certain temperature, a certain brightness, they disappear, they turn into another kind of star, and we don't see them when we observe them. This is now an example of a nearby galaxy. So brighter stars are up here in the diagram, fainter stars down here. And these are cooler stars. So here's this red giant branch. Our sun will eventually reach the red giant branch. And once these stars reach this particular brightness, then they fall down onto what is known as the horizontal branch shown here. And what that means in a practical sense is that when we go out and we observe these objects in the outer halos of galaxies, that we can measure, in fact, thousands of them in the halo, but we don't see many stars above the brightness of this tip. It's very easily identified. We can measure a peak and a discontinuity from where this luminosity, it's called the core helium flash, resides. And so our idea was to use the Hubble Space Telescope and to go out into the halos, the outer regions of nearby galaxies. These are images taken with the Hubble Space Telescope. And so I think the telescope operators were worried that we'd missed our targets because we didn't sit on the galaxies themselves, but that was deliberate. And the advantage here is that in the disk, as we saw before, there's lots of dust. There are new stars that are being formed. And so we have to worry about how that's impacting the brightnesses of the stars that we're trying to measure. With Cepheids, we have no choice, because Cepheids are young stars, and we only find them in the disks of galaxies, certain types of galaxies that are still star-forming objects. And so these stars have this advantage that they're both away from the dust, but also there are far fewer stars out here. And when you get close in to the inner regions of galaxies, then the stars themselves start to overlap. And when you are trying to measure how bright they are, you can have real difficulty trying to separate them and get their brightnesses very accurately. So a lot of advantages to this other method. And then to step out to the distant universe, we use these bright supernovae that we can see almost all the way across the universe. And this is a whole lecture in itself. We had a Carnegie Supernova project going for over 10 years. And I particularly want to acknowledge now Chris Burns, and some of you may have seen him talk here, and also Mark Phillips, who was the director at Las Campanas in Chile for many years, and a large group of us here at Carnegie that extended the Hubble diagram. So this is another Hubble diagram similar to what Hubble made originally, but now calibrated using the tip of the red giant branch and moving out into the distant universe. And so we had hoped by doing this different kind of measurement that we would either get 67 or 73 and we would resolve the current debate. So what happened? We landed flat in the middle. And in fact, we overlap in uncertainty with both of the different kinds of measurements, which is, well, that's what we got. And there are actually serious astronomers who said to me, what did you do? I mean, it's like, why can't you get one or the other? Well, you don't change your measurements to suit the data. You make the measurement and see where it falls. And this is a very famous astronomer, actually, so it's interesting. So here we are in the middle, and you can see that our uncertainties do overlap pretty well with the measurements now of the microwave background. And they also agree reasonably well with the Cepheids, so we can't really distinguish between them. But I think if we had done the key project using these tip of the red giant branch stars and then made the measurements with Cepheids, we would probably be saying, what's wrong with the Cepheids? But at this point, I think it's too early to say how this is going to come out. So what do we do? Fortuitously, Christmas this past year, a new telescope was launched, the James Webb Space Telescope, and you may have seen a lecture on that, read about it in the newspaper, but this is a spectacular new telescope. There are 18 mirrors, gold-coated, and this is a telescope that's sensitive to infrared radiation. It has a sun shield. The telescope has to be cooled. It's actually measuring essentially heat radiation. And so there's a 5-layer sun shield here. The thickness of each of these layers is comparable to the width of a human hair. I mean, it's a spectacular instrument. And the 5 layers had to unfurl in space, as did all the mirrors, as it was traveling it out to 1 million miles away at a place called the Lagrangian 2 point, where it now is located, and the instruments have been calibrated, or being calibrated, and it's being fired up, and we're hoping to see first science results this summer, which pretty amazing. So this sun shield has an SPF, in case you were wondering, a sun protection factor of 1 million. And it's pretty amazing. So this was something early on. I was fortunate to be an astronomer that was invited to be on the first scientific advisory committee for the telescope. And we went to the Goddard Space Flight Institute, and they showed us an animation of what had to happen in space as all the mirrors were going to unfold in space, and this sun shield was going to miraculously open, and the astronomers in the room, we looked at each other and we thought, this is just nuts. This is never going to work. This is 25 years ago. And it did. It did. And it's been an amazing success so far. So they started releasing images. This was the first one of a calibration star, and they were all over the place. And then they got them in the center of each one of the 18 mirrors a few weeks later. And this is a recent image from earlier in the month, a comparison of a region imaged by the Spitzer infrared telescope compared now to the mid-infrared instrument on JWST. And again, you can see this spectacular resolution. And there are images now, so they took a calibration image, and then there are all these galaxies that showed up that have never been seen before. So these are test images. If you can, if you see astronomers drooling right now, this is why we can't wait to see what this telescope is going to do. It's going to be amazing. So why is it so good? If we look at, this is the Eagle Nebula. So this is a region in our own Milky Way galaxy where stars are being formed. It's literally a stellar nursery. And inside these columns, I think the longest column here is something like 60 trillion miles high. This is small. This is a small region in our own galaxy. These numbers are truly astronomical. And this is what it looks like in visible light. So this is an image, composite image, beautifully colored by a space telescope. And this is what it looks like in near-infrared light. So this is one of the reasons why we make observations. This is early work that Barry Medora and I did before Hubble was launched to show that if you observed in the infrared, you could penetrate the dust in a way that you can't do with visible radiation, because the size of the dust grains is comparable to that of visible light. The infrared wavelength is much longer wavelengths, and it essentially doesn't see the dust. It comes through, so you can see many more stars in this near-infrared light. And then when you go to the mid-infrared, you're actually seeing light that's being re-radiated by the dust. So now you're studying the dust in the mid-infrared. So you have these different windows that you can study the universe. And one of the nice features of the telescope, it's a large mirror now in space, and as light is traveling to us from the distant universe, it gets stretched by the expansion, so the wavelength gets redder, and it essentially allows us to look back in time to what galaxies were like in the early universe as we observe in the infrared. And so it's like a time machine. It's one of the amazing things about astronomy is we really do get to look back in time. And this telescope's going to allow us to see the first black holes that are forming in the universe, the galaxies as they're actually forming. We'll witness the first galaxies being formed and literally see the cosmic dawn. And so, again, now we can improve our measurements of the distances to galaxies. And our proposal, which was awarded time by the Time Allocation Committee for the first cycle, it's going to let us observe Cepheids in nearby galaxies. It's going to let us observe these red giant branch stars in the same galaxies. And then it's going to let us observe another type of star, which we've been working on completely independent of those two, all in the same galaxy. So if there are systematic effects in any one of those or all of them, if they don't agree, we'll get a good measure of the uncertainty. If they do agree, we'll have a lot more confidence in the measurement that we make. So whoops, I'm back. How do we resolve the tension? I think the future really does look bright. We still have a large program with Hubble to continue measuring in the nearby universe stars, both the tip of the red giant branch, these bright giant branch stars, as well as a new method, a yet new method that Barry and I have been working on, which no one else, I think, except for the two of us know about right now, which we're really excited about because it's something we can do with Hubble. I haven't mentioned, and it's almost, it is certainly an entire lecture by itself, but there's a satellite called Gaius being run by the European Space Agency, and it is measuring nearby stars in the Milky Way, 1.5 billion stars, in fact, in our Milky Way. And it's making these measurements, and it can determine distances based on geometry. And so as the Earth is going around the sun, if we look out at the sky, at different points in the orbit of the sun, we're looking at stars in the galaxy from a different vantage point, depending on where we are in the orbit. And it's literally the most accurate way of measuring distances. You just need high school geometry, it's angles. And right now, they're still working on calibration, and there are issues with, as the telescope moves and as it's pointing at the sun, there are temperature variations, so there's an adjustment in the calibration, and there's some uncertainty with respect to the quasar distribution, really distant objects that have been measured very well. But that will be solved in the next few years, and that will apply a much more accurate calibration to the red giant branch stars and the Cepheids themselves. So that's one part of it. And then the next, of course, is JWST and our ability to look into the infrared where the dust effects are smaller. The resolution will be higher, so if there are crowded stars, the Cepheids themselves will be able to determine that. And then there are other kinds of issues having to do with how much the stars have metals in their atmospheres, which also can affect how bright they are. So I think the future is looking very bright. And I would say stay tuned. I think we're going to have a lot to say in the next year or two as these new data become available. And the Giant Magellan Telescope in the early 2030s will be working very much in a complementary way with the James Webb Space Telescope. One of the things that we were delighted to see was that this, by the way, is what it was doing on its way to its million-mile-away orbit where it's now parked. Unfurling the sun shield and there it goes, and the mirrors. But because it was such a magic launch, almost perfect, they saved fuel, and the goal was to have a 10-year lifetime. So they thought they could for sure get a 5-year lifetime, but it's now almost certainly going to be a 20-year lifetime. So there will be overlap. GMT is likely to last for half a century or more. Probably more. It's hard to get rid of, I suspect. But anyways, I think the future is extremely bright, and I'm really looking forward to it, and I'd be happy to answer any questions you might have. So thanks very much. Yeah.
We do have mics back there in the corners if people would hear it.
Yeah, it's blinding.
What telescope or telescopes were used to create the age of the universe map?
The age of the universe map?
You mean the cosmic
yeah. So the first one that I showed was from a satellite called WMap, which was the Wilkinson Microwave Anisotropy Probe, is what it stood for. And that was a US project. Dave Wilkinson was an astronomer who had worked on the microwave background and had done a huge amount in the field. He actually died. They showed him the first map. He at least got to see the first map, but he wasn't able to participate in the actual analysis. And then the second one was from the Planck satellite, which is the European satellite, and that's the most recent one.
Wendy, that was a great talk, as usual. Thank you very much. My question is, you alluded to the fact that the two different measurements with the Planck and the Hubble telescope are essentially in two different epochs, at the very beginning of the universe and more recently. So is it possible that the Hubble constant is simply changing in time, and what implications might that have?
Yeah, that's what I was showing in that earlier slide, that something might have happened on the way in between the Big Bang radiation that we're measuring in the CMB and now, or maybe even earlier. So it's very interesting because since this discrepancy has arisen, hundreds, probably even more, of theorists have jumped on this problem to try and understand, could there be missing fundamental physics? Because if it's real, it's really exciting. We're learning something new about the universe that we couldn't learn in any other way right now. And what's really interesting is, as the measurements have gotten more and more precise from the microwave background point of view, so those peaks that I showed you, early on there was some wiggle room. And so, for example, one way you might solve this is to have an additional what they call dark radiation. Could be a relativistic particle, like a neutrino, an extra neutrino. And so that seemed like a very plausible explanation, and there's actually a degeneracy. You can play the value of the Hubble constant off against the effective number of neutrinos. But as the measurements have gotten better and better, that became really hard to do. And then right now, I didn't say much about dark energy, but the dark energy is what's causing the universe to accelerate. And since we don't understand the origin of the dark energy, we don't understand whether it varies with time or redshift, that is a plausible explanation, or it was. But the difficulty now is that there are really precise measurements that have been made both using these type 1a supernovae with a very wide redshift range, and also something called baryon acoustic oscillations, which are indicative of the fluctuations in matter, not the fluctuations of radiation that I just showed. And those don't allow much of a change as a function of redshift, that is not what you would need to explain this difference. So one by one, a number of these things has been ruled out. So now where the theoretical community is at is saying, okay, well, all of these other measurements now have been ruled out by other observations. Go to a place where we can't yet measure, right? So before the surface of last scattering, where we see the radiation from the Big Bang. So there's something people are referring to as early dark energy. And so you would have some sort of field, like the inflaton that drove inflation, and it would be operational before recombination, and then it would have to disappear where before you could see its effects on the peaks that we were actually measuring. And so we'll see. It will have a signature in the polarization of the microwave background temperature and polarization of the signal. And if it's there in the new experiments that are coming, like the Simons Observatory, and there's something called CMBS4, it'll be a whopping signal if it's real. So yeah, we'll see. But potentially is extremely exciting. It could be new physics, or it could be something we don't understand. But either way, we need to make these measurements to determine. And I think either way, it's interesting. If we confirm the standard model, that's also a really important result. If we find something new, that would be great.
Yeah, that was very similar and connected to the question I was going to ask for. The first one is, turns out if you go to Wolfram Alpha, where it does computational inquiries, you can take the age of the universe times the Hubble's constant. The answer is 1, which would imply Hubble's constant is the reciprocal of the age
That's correct.
of the universe in seconds.
That is correct. That is essentially what it is. And if you notice that units are kilometers per second per megaparsec, it's essentially 1 over time.
Yes.
And if there were no dark matter or dark energy, if you didn't have to worry about the other components in the universe, that's exactly what it would be. But you also have to factor in the cosmology to determine the age. But interestingly, it comes out very much the same, 13.7 million years.
Has any of the theoreticians you've talked to considered the possibility that the Planck units are covariant with time, because all the physics equations still work as long as they maintain the ratio between the Planck length and Planck time, so that the speed of light's constant? and that it would covary with the Planck mass and the Planck charge.
Believe me, the theorists are looking to every conceivable possibility. I mean, it is a real mystery right now. And, but so far have not been able to come up with an explanation for what it actually is.
At the Goddard Flight Space Center, Kashlinsky is the guy's name. He's discovered this thing he calls dark flow. Have you heard of that one? Mm-mm. It's where he's seeing this characteristic flow of the galaxies at different distance depths into the look-back time. And he's detecting a drift towards a certain part of the universe. And it's as yet unexplained, unless, of course, the universe is not flat, and that the second is not constant, and so the universe would have a positive curvature, in which case it's spherical, and the point at the opposite side of the hypersphere would be one of these depths into the look-back times. And they just so happen to be the square root of half a pi, the square root of pi, the square root of 3 halves pi, or 2 pi.
Yeah, I think, these are the kinds of things that will become clearer with time as measurements become sharper and you can make these measurements in different ways.
I'd be really interested in having Hubble look at those distances in certain parts of the sky to see if the observation is that the galaxy is either converging towards a point or emerging out of a point. And he literally says in his documents, they can't tell if they're coming or going. Mm. But they're definitely...
There are, very large-scale maps now. There's a new facility called the Rubin Observatory that's going to be mapping the sky every few nights, very large scale. And there's a spectroscopic project that is measuring millions of redshifts or velocities. So our maps of the universe are, another area that's going to be exploding in the next decade that really will shed light on these kinds of things.
Thank you.
Hi, that was a very nice lecture. I'm not an astronomer, so I have a question about the cephalids. Why is it that the intensity of the light varies with the cycle length? What are these things?
Yeah, it's interesting. And Henrietta Leavitt didn't know about it at the time, but it turns out that these stars are actually, their outer atmospheres are actually moving in and out. So the star is pulsating with time. And so literally as the star is getting brighter, the luminosity goes as the radius squared. So as the star gets bigger, the star gets brighter. And there's a region in the atmosphere that's going from singly ionized to doubly ionized helium. So as the star is expanding, the star is getting cooler, and then when it gets cool enough and the radiation no longer is ionizing the electrons, then the gravity takes over and the star collapses, and then it gets hotter and the cycle repeats. So it's like a heat engine. There's a pump, and it just keeps repeating.
What is the cycle lengths? What's the variability in these cycle lengths that you can actually observe them? We're talking about hours, days, months, years?
Yeah, days. So they typically have periods from about 2 days. They can go up to over 100, but the longer period ones we don't understand as well. But this really sharp relation that we see that I showed you of Henrietta Leavitt's, the Leavitt Law, it goes from about 2 to 60 days or so. That's where we observe most of them. And that's where, in fact, most of them reside. The longer period ones are quite rare. They're higher mass, and there aren't as many high mass stars.
Thank you.
That's it. That's it.
Oh, sorry, you're calling somebody else. I was calling somebody. Good, go ahead.
Okay.
There.
No? Oh, you just moved. Okay.
Could you comment really quickly on whether gravitational waves interact with your work?
Really quickly, no. So gravitational waves now have been measured for the first time since 2017. The LIGO detector got working, and you can measure gravitational waves, for example, if you have two massive black holes that are orbiting each other. and they're actually distorting space-time. And so you get these wiggles in space-time. There are gravity waves that are expected from the early universe that we can't detect yet. LIGO is working mainly is discovering black holes sort of a few tens of times the mass of the sun, and neutron stars, neutron star binaries, or binary black holes, neutron stars, or black hole. And there will be eventually a satellite called LISA that will measure massive black holes, and that will be launched, I don't know, 2040, I would guess, but, and that will measure the really massive black holes in the universe. But no, you need really massive objects that are moving to distort space-time, measure it.
I don't understand at all how you can measure distances using the Cepheid stars.
Okay. Want to come to one of my lectures? To really explain it will take longer, but let me try again. What's that? Captive audience. You have nothing to do this evening, right? So the relationship that I showed you, the Leavitt Law, what it tells us is that the brighter that the Cepheid is, the slower its atmosphere is moving, okay? Now, if we can then, for example, with Gaia, the parallax satellite, measure a Cepheid in our own galaxy, where we can get its distance, so we know what the distance to a nearby Cepheid is. Then, and we measure a Leavitt Law in the galaxy. Then we go to another galaxy, and the galaxy is far away, so its Cepheids are fainter than the ones that are nearby, right? Because just like a lamp that you're looking at the distance, it gets fainter. And so there's something called the inverse square law of light. What that means is light has a property that the brightness falls off as 1 over the distance squared. So if you compare the brightnesses of your distant Cepheids, you have a period luminosity relation for your distant Cepheids, you have a period luminosity for the ones you know the distance to, then you can measure the distance because the luminosity, the brightness of your Cepheids in your target and your nearby Milky Way sample falls off as the distance squared. So the distance comes out of that comparison of the brightnesses. And the reason that it works is that the period doesn't care what the distance is. So you have one quantity that's dependent on distance, one quantity that isn't, you compare them, and then with the inverse square law of light, you get the distance. Now that's the simplified version, that's what Hubble did. The problem is you have to worry about dust, you have to worry about abundance, you have to worry about crowding, you have to worry about all sorts of other things that, turbulence in the Earth's atmosphere that makes it harder in practice. But in principle, it's a very simple principle of inverse square law of light. That help? Okay, now you can come to my class. I think John's pointing at you.
So I'm brand new, and so I came to the lecture out of interest, and the title is Crisis in Cosmology, and I don't see a crisis.
So the title had a question mark, and I don't see it yet either, so you got the point of the lecture. It may be. I think we will learn something in the next few years, as I pointed out. But I think until we really can establish, based on a number of different measurements, that this discrepancy is real, then I don't see it yet as a crisis. There are others who disagree with me violently. Thank you. Hi, how are you doing? It's nice to see you. Sorry I didn't, I saw you move and I didn't.